All right, so let's take a look at what's next, what's called a residual plot. One of the first principles of data analysis is to look at an overall pattern or striking departures from a pattern. Remember that when we're looking at data itself, we're looking for patterns. We need that to try to do the interpretation. A regression line describes the overall pattern of a linear relationship between two variables. Very important. Remember, our line of best fit, a regression line, is to look at the linear pattern here. So we can see the parts of that by looking at residuals. So what we can do is we can do what's called a residual plot. And a residual plot is a scatter plot of residuals against the explanatory variable. So residual plots help us assess how well a regression line fits the data. So we basically plot the x variable in the x's and the residuals in the y to try and see what we have. Let's take a picture of this. So here's what we have, back to the truck example. This is what we have as miles driven, right? So this is normally what we have. This is the X, miles driven, and the Y, price in dollars. But what we can do here is, here we have an actual residual plot. So what this has done is we still have our explanatory miles driven, but what we've done is we've done the residuals here. Now I'm going to show you something really cool. I'm going to pop out of my presentation real quick. And then we can talk about a residual plot here for the McDonald's fat data. Okay. So really what I want to show you here is that this line of best fit and the residual plot, they have a really nice relationship. See this line of best fit here that's coming down, that's decreasing? In a residual plot, this line of best fit kind of becomes our horizontal axis. So if we take a look at this, and I'm just going to rotate this a little bit. So, and look at this line here. The patterns that we see here in our actual scatter plot are kind of more to scale in the residual. So that's what it really does for us. It lets us take, with a residual plot, our line of best fit as our horizontal axis, and let us take a look and see that pattern. I can kind of see a little bit of a sinusoidal. Maybe it's a little bit of a curve here. And I'm probably just trying to look for that so I can say the cool word sinusoidal. But see, I still see that kind of bend here, and here. So a lot of times when we're looking for a residual plot, we can think about it as it just being the line of best fit, and here what we have. And that's a nice quick way on a test too, to try to line up a line of best fit with its residual plot, is to kind of do that little shift. And let us take a look there. All right. Let's going to jump back in and do a residual plot for the McDonald's data here. All right, so what's really nice about when we have this data is that when I ran this line of best fit, it may not look like it because something happened in the background, but all the residuals were actually created for us. That was pretty neat. So if I go back to my stat and I go to edit the different lists that I have here, I can see all my lists here, right? But if I go into stat and I go second lists, what I can see down here is I have what's called a resid. So I can see that I can put my residuals, whoops, sorry. I can go here and I can see that residual list. Now, I can, if I want to, just go to second list, residuals, and go here and see that kind of listed out. These are all my residuals that I have, and that's kind of hard to read them, right? Those are all the residuals. So every time I make a line of best fit, the residuals are calculated. So what I like to do is I like to go into stat, edit, and I like to put my residuals next to my data points. So I'm going to go over here. Here's my X. Here's my Y. I'm going to go up, and I'm highlighting right now, highlighting list 3. Now I'm going to go to second list, and I'm going to put the residuals in there. And what that does is that automatically lines up all the residuals. Remember when we were back, I'm going to go back here to our McDonald's here. We had to find the residuals for the Big Mac that was at $45.29. Take a look, $45.29, And then what we have here with a little bit of our rounding error is the 0.787. There's a nice residual there. It's a little bit more precise what we have. So we have the data points and the residuals here. That's really nice that our calculator can help us do that residuals. So what does residual plot look like? Well, remember that our residual plot is going to have the X value here and the residuals. So I'm going to go back. I put my residuals here in list 3 to my stat plot. I'm going to go to stat plot on, and I'm going to have my residuals here I have stored into list 3. So I can go to second list, and I can pick list 3, or if I forget where they go, or I didn't put them in list 3, I can just say residual here. So residual plot is X versus the residuals. Zoom to my stat plot, and here's my residual plot. I can now trace, so I can go through and look at my X values and see what the associated residual will be. Again, that's nice. Here's my 45, my Big Mac, and I can see the residual would be negative 7.87. So in a residual plot, we can look here and get those values. What we're really looking for here is we're looking for any pattern that we can see. If it's a curve, we know that maybe there's a curve in the original data, and a residual plot tells us that the line, a linear model, is not appropriate here. So that's how we look for a residual plot to try and figure that out. So let's take a look here at another example. Here's an original data plot where we see an obvious curve. And we can see that in the original plot, it makes it more profound. So you may not see that curve may be so small that you can't see it in the original data, but a residual plot really makes that pop. If you can see any of our, any curvature here in the residual plot, then that warns us we might have some danger here, and we may not have an appropriate linear relationship that we can model. So way back when, I can't remember if we have done this yet, but this is our Monopoly scatter plot. So this is a scatter plot of how many points you are around, or I'm sorry, how many spots you are around a Monopoly board. And then what you have is what the value is. So we have some outliers here. It doesn't matter where you are in the board, the railroads 1, 2, 3, 4 are always the same price. So we see that here. And then we also have the utilities here. So we would take a look and say, is the linear model appropriate here? Well, we kind of see a weird pattern here. It's not a nice one here. It kind of goes up and down. We're not seeing that straight model here. So it might be something that we're worried about. Again, if we took a look at our model here and here, we can see that simply our model kind of rotated to make that flat, is what we see for the residual plot. Okay. So that's taking a look at it here. Notice that when we do our models, when we do our stat calculate line of best fit, we've been talking about R and we've been talking about R squared. And before, when we have R and R squared, we were using R to talk about the correlation coefficient. Well, R squared has a really cool name. It's called the coefficient of determination. If you're looking for a cooler variable than that, you just need to stop. There really isn't one. The coefficient of determination. The coefficient of determination is the fraction of the variation in the values of y that can be accounted for by the least squared regression line, the relationship between that y and x. And we're going to interpret that a little bit more in context to tell you that. But that is really cool. Okay, R squared, the coefficient of determination. R squared basically tells us how much better the least squared regression line does at predicting the values of y than simply guessing the mean y for each value of the data set. So let's go back to the price in dollars and the miles driven. For this data set, R squared was 0.72 or 72%. Okay, so what does that mean? What that means is, well, first of all, I guess if it's 0.72, then what is R? And you know, that's pretty easy, right? Because if we know r at 0.72, that's r squared, right? Then we'll just take the square root of that. Oops, got my imaginary number in there. 0.72. Ah, there we go. All right, so there's my r, about 0.84. Okay, so that's pretty easy, just taking the square root. And then, so we want to interpret r squared. That's new to us. What does r squared mean? So here's how it looks. Here's what it looks like. 72. 72% of the variation in price is explained by the linear model relating miles driven and the price of the truck. That's pretty cool, okay? So we're saying that 72% of the variation in price is explained by the linear model relating to miles driven. So, okay, well, you're like, well, 100% minus 72, how do we explain the other 28%? And that can be a variety of things. That could be the options that are on the truck. That could be the brand of the truck. In this case, this is Ford F-150, so that's not something we do here. So a lot of times it can be in the region that you're buying it from. But a lot of times I'm gonna guess that it's gonna be the options that you put on a truck, right? The size of the engine, or if you have safety features, or if you like those big rims, right? If you have the moonroof, if you have the tow package. So this is a pretty good model. And we know that from our R being 0.84, that's pretty close to 1. That's pretty strong. It's a strong relationship here, but R squared is really nice. It really tells us the percent of the variation in price that we can attribute to this linear model with miles driven. So that's really neat. And of course, obviously, we're going to see that if we have a stronger R squared, we're going to have a stronger R. And doesn't that make a lot of sense that if we have a very, very, very strong correlation, then our model is going to do a really good job explaining that association between Y and X. So we really don't have to worry about how to do those by hand, the R squared. Another thing we don't have to worry about by doing by hand is called S, and that's the standard deviation of the residuals, okay? So S is going to be given to us in almost every case now. So if we want to assess how well the line fits the data, we need to consider the residuals for the observation, not just one. We take a whole collection of the residuals, and then using the residuals, we can estimate the typical prediction error. Now, where did we hear typical before? We heard that in standard deviation. Standard deviation with a typical amount that an entry can vary from the mean, right? So if we take a look at that and we want to see the typical amount that it can vary. So if we take a look at S, it's the standard deviation of the residuals. So what's the typical amount that we have for residual? And remember, a residual is an error in the prediction and the actual. So this is really the typical error. So the standard deviation of the residuals, or S, is the typical prediction error. So let's go way back in section 3.1. We were talking about points per game and the number of wins down the SEC, right? And so we have this scatter plot. So we bring it back. Here's the equation, the least squared regression lines for that scatter plot. Also, let's see, we see that S is equal to 1.24 and that R squared is 0.88. So we're going to talk about going back to what does this all mean? So kind of practicing here, again, this data set, what does all this new stuff mean? And also we can see the nice residual plot next there to the line as well. Okay. So first of all, let's calculate and interpret the residual for South Carolina. They scored 30.1 points per game and had 11 wins. Okay. So the predicted amount for South Carolina is, well, remember that Y hat, or the predicted Y, from our line of best fit on the previous slide, was negative 3.75 plus 0.437 times the points, or we're going to put the points in of 30.1. So that is a predicted wins of 3.4 wins. Now, the residual is actual minus predicted. So what we had was we had an actual wins was 11 minus predicted wins of 9.4, so that was a predicted 1.60 wins. So South Carolina won 1.6 more games than was predicted based on the number of points they scored per game. Let's consider the linear model. Is it appropriate for this data? So we take a look at this data here. I don't see any obvious patterns. I'm looking for curvatures. I'm looking for bends. It kind of looks like it just spread out or as a cloud. So I'm not too worried about it. So basically I would say because there's no obvious pattern in the residual plot, the linear model is appropriate. Let's interpret the value S is equal to 1.24. Do you remember what S is? All right, I'm going to give you a pause. Think about this yourself. Pause the video and answer this before I show you the answer. All right, don't just wait. Hopefully you've tried this yourself. Think about what it is. Okay, here we go. When we're using the least squared regression line with X points per game to predict Y number of wins, we're typically going to be off by about 1.24 wins. So again, S is the standard deviation of the error rate of the residuals. So typically that's going to be how far our model is. Remember that the word typically is used in standard deviation, okay? It's not the average. We can't use that. It's not the average. Average goes with our slope. We have to be very careful. We're using average with our slope here. Typical, or the typical amount, is with our S's here. And then R squared, the coefficient of determination, is 0.88. What did that mean? All right, answer it for yourself. I'm going to give you the answer. I'm going to click it soon. Try to think about what it is first. All right, here it goes. Hope you've thought about it already. About 88% of the variation in wins is accounted for the linear model relating wins to points per game. Okay, so that's good practice trying to run between those two there. So this is a good time to take a break and stop and work on homework number 5. In homework number 5, we're really working to construct and interpret residual plots to assess if linear model is appropriate. Thinking really a lot about doing that on our calculators. Using the standard deviation of the residuals to assess how well the line fits the data. And then using R squared to assess how well the line fits the data. And then interpret the standard deviation of the residuals. That's S and R squared in context. So if you're stopping to do your homework here, kind of look at the video, see where we stopped, and then come back and join us.